The partition functions that we've been talking about up to this point are something that we might actually more accurately term molecular partition functions. Now, why I'm specifying this is because the energy levels that we're using to build the partition function are based on the energy levels of an individual molecule. So in other words, those little E sub j's are really relevant for a molecule, not for a larger system. So what I'm going to do in this video is talk about how we can generalize these molecular partition functions to talk about a partition function that might be relevant for the whole system. Now, before I do this, I want to simplify some of the notation that we're using. These summations that we've been using to create the partition function are implicitly summations over the levels, that is, the energy levels that the molecule can have. And that's why we've included these degeneracies in those levels, because a particular level may have many states that have the same energy. And what we're going to do instead is we're going to make this into a summation over states. So now each state has an energy. Some of those states have the same energy as another state, but it's not going to matter because we're going to be summing over all of the states. So it's a little bit of a subtle change. But by making that change, now I don't have to worry about that factor for the degeneracy. It's implicitly included now because I may have more than one term in this sum that actually corresponds to the same energy. Now what I want to do is start with a couple of these partition functions for molecules and see what happens when we begin to multiply them together. So for example, if I have two molecules and I multiply their partition functions together, I'm going to end up with each one represents a sum, so I'll have 1 as I equals 1 over all states, e to the minus e sub I over kbt. And let's say this one is for molecule 1, so I'll use a little superscript to indicate that. And then the second one will be a sum over all states for molecule 2. And again, I'll e sub j for molecule 2 over kbt. All right, now I can combine two summations like this and basically make it a double summation. So I'll draw it like this, where I'm summing over all the possible states in each of these molecules. But what I'm going to end up having is this factor multiplying by this factor. And whenever I multiply two exponentials to each other, with each other, what I'm going to end up doing is summing the two exponents in the result. So I'll have e to the minus e sub I of 1 plus e sub j of 2 over kbt. All right, so you can see that this is a little bit clearer way perhaps of writing the product of these two molecular partition functions. But the thing that I've gotten out of this is the sum of these two energies, and I could in fact claim that that sum of those two energies is in fact the system energy for those two molecules. All right, so in effect what I've gotten is an expression that's very much like the expression that I had here for a single molecule. But the thing up here in the exponent is the system energy, not the energy of an individual molecule. Now what about the sum over states? Well, basically, if I'm summing over all the possible states that each molecule could have, that's really the same as summing over all the possible states of this system of two molecules. So I've basically taken care of that with this double summation. If I want to convert this to a summation over system states, these two summations will cover my basis for that. So now I want to think about doing this for a whole series of molecules up to n total molecules. And when I do that, I hope it's not a stretch for you to imagine that now I can turn this into a summation over all of the system states, because I've included all the possible combinations of these molecules, and it's going to be e to the minus e sub j, and this is the system energy divided by kbt. So now I've got something that looks very much like my original expression over here for molecular partition functions, but now it's talking about a whole bunch of molecules together. Now, there is one additional thing that I have to do here. In some sense, I have overcounted states. Okay, let's suppose in this case of two molecules, I have molecule 1 in state 1 and molecule 2 in state, well, let's make one up, state 17. All right. I also have created a term where I've got molecule 1 in state 17 and molecule 2 in state 1. All right, but both of these really represent the same system state. So in effect, I've double counted all of the system states by doing this. And when I have n molecules, I've actually overcounted them by a factor of n factorial. So we're going to see again the need to introduce a factor of 1 over n factorial so that we're not overcounting. We're basically taking into account the indistinguishability of these molecules from one another. All right, so when I do that, now I can write a system partition function. I'm going to use a capital Z for that, and I apologize, a capital Z may not look much different from little z for me, but nevertheless, it's capital Z. So this is going to be, in effect, equal to this, where I've got the system partition function, and these little z's are molecular partition functions. So if I raise a molecular partition function to the power of the number of molecules in the system, and that could be a really large number, and then divide by 1 over n factorial here, then what I get is the effective system partition function. So I hope that that makes some sense. And this is, we're going to mostly focus on molecular partition functions, but there will be occasions when we will need to look at a system partition function. And so this is the way that one converts between them. All right, now let's look at an example of what we might want to get from a system partition function. Let's suppose we have some property, okay, of a system, and that property is denoted by the letter A. Okay, that A could be energy, or it could be, some other quantity that characterizes the system. And what I want to know is I want to know what is the average value of that property A for the system. Okay, now I'm going to use this sort of awkward notation. Another notation that's commonly used for average value is just to put a bar over the variable. However, I've started using this to denote molar quantities, and I want to continue to use it to denote molar quantities in the future. So I'm going to go to this awkward notation for average values. All right, so how would I determine the average value for some property? Well, one way I could do it is to say, okay, this property can have different possible measurements. Okay, let's say A sub j represents one of the possible measurements that I could have on this property. Now, what I would want to know is what is the probability of measuring this value? Well, it would simply be the probability of being in this state j. And now if I sum over all of these possible probabilities and values, that would give me the average value. So it'd be kind of like if I wanted to know what is the average height of women in the world, I would want to find out, well, what is the probability that women are 5'1", and multiply that by 5'1". What is the probability that they're 5'2", and multiply that by 5'2", and in that way I could determine what the average height of all the women in the world is as long as I know these probabilities. But these probabilities are something that we get from the partition functions. So now if I use my expression for probability, and let me write it over here, probability of something is just going to be the number of a number of molecules that are in state j divided by the total number. All right, but this is also equal to this e to the minus epsilon j over kbt divided by the partition function. I can use that to basically determine this average value for this property A. So in the case of a molecule, it might be that A sub j is multiplying by e to the minus epsilon j over kbt, and then I have to divide by the partition function to make that a probability. All right, so we can do the same for system if we simply do it this way. So this would be e to the minus system energy over kbt divided by the system partition function. All right, so this is going to give us a prescription for evaluating the average values of different thermodynamic properties for a system using the system partition function. Now, I want to illustrate that. I'm going to use a different sheet of paper here. I want to illustrate that for determining the average value of energy. All right, and I'm choosing energy for a specific reason because there's a really cute result for this. Okay, so I want to know the average value of energy. And I know, for example, that the partition function of a system is written in terms of the energies of the system like this. Now I want to rewrite this expression in the exponent in terms of that old parameter beta that we got when we found the most probable distribution. So I'm going to really write this like this: e to the minus beta e sub j. Now it's easier to do it this way, and you'll see why in just a minute. Let's suppose that I have some function e to the ax, and I take the derivative of this with respect to x. Well, that would give me a times e to the ax. That would be the result of the derivative. So now if I take this expression for z system and I take the derivative with respect to beta, oh, interesting. Okay, I'm going to be taking the derivative with respect to beta of the summation e to the minus beta ej, and that's just the same as taking the derivative of each of the terms in that summation. And now from this formula up here, I can write this as the sum over j of the derivative of this, which is going to give me a factor of minus e sub j times e to the minus beta ej. Okay, I'll bring the minus sign in up front, so it'd be minus the sum of ej times e to the minus beta ej. Okay, well this looks a lot like the formula that I need to find the average value of energy. The average value of energy would be 1 over the partition function of the system times the sum over j of ej e to the minus beta ej. So this summation here is just the same as the summation here. But now I've done this in terms of taking the derivative with respect to beta of the partition function itself. So in other words, this thing is just, and I've got a minus sign here, so I have to pay attention to that. This is just the minus of the derivative of the partition function with respect to beta. So I can write the average value of the energy is negative derivative with respect to beta of the system partition function. Okay, oops, and I left out this factor of 1 over z, so let's put 1 over z here. Okay, that factor of 1 over z is important because I can actually write this in an even more compact way by taking advantage of the following relationship. Let's suppose I have the logarithm of some function of x, and I want to take the derivative of that logarithm. Well, if I take the derivative of the logarithm using the chain rule, I would find that this is equal to 1 over f of x times the derivative of f with respect to x. All right, so here I've got 1 over f of something times the derivative of that something. So in fact, this is just the same as dd beta of log of this system partition function. So oftentimes you'll see, in fact, that the average energy for a system might be written in this very compact way as minus d log system partition function with respect to beta. All right, so this is, I'll say, a formula that we will want to pay attention to because it gives us a very interesting and compact way, if we know this partition function, of calculating the average energy.